In the previous video, we discussed the identification challenge that happens when there is no restriction on coefficient heterogeneity and when there is no state that's totally unaffected by Medicare. We can turn to a difference in difference style estimator that has been proposed to amend the 2-effects estimator and see that this identification challenge will still apply. In the paper, we call this exposure adjusted difference in differences estimator, which first calculates the difference in differences in the outcome between state S and S prime, but then adjusts this difference by the difference in differences in their exposure to Medicare. It's able to focus the comparison between two states S and S prime at a time, so to some extent could address the conflation issue with two-way fixed effects estimator. Matan and Foy call this estimator a walled difference in differences estimator because it consists of the ratio of the difference in differences estimator for the outcome to the one for the exposure. As with the 2-effects estimator, this exposure adjusted difference in differences estimator can still be centered outside the range of true coefficients, including in our numerical example, when both states S and S prime are affected by Medicare and when beta S and beta S prime can differ arbitrarily. Now, there are several solutions for this identification challenge. First is to impose structure on the heterogeneity of the coefficients beta S. For example, suppose a researcher is willing to assume a linear relationship between beta S and X as 0, as we saw in the numerical example earlier, but does not know the value of the parameter lambda that governs this relationship. Then it's possible to substitute the expression for beta S using the linear relationship between beta S and X as 0 and still arrive at a linear panel model whose unknown parameter would be lambda. It can then be estimated by a 2-effects estimator, and thus allowing the researcher to estimate the average of the coefficients beta S. Another approach is to impose bounds on the variation in coefficients and the mean error term. One example is a paper by Metsky and Pepper, who calculates the implied bounds on the average treatment effects on the right to carry laws on gun violence. Recent literature has focused on the solution when we actually have access to more data, say a totally unaffected state where prior to Medicare, it already had a universal coverage for the elderly, or when there is a control state that's not affected by Medicare. For illustration, I'm going to focus on this last case when there is a totally unaffected state. Suppose that in state S prime, Medicare had no effect on insurance rate. Then using this unaffected state for comparison, we would arrive at an exposure adjusted difference in differences estimator that would take us closer to the classical difference in differences setting of Card and Kruger, because we're just adjusting the difference in differences estimator by the exposure of the state S. In this case, we can show this difference in differences estimator is an unbiased estimator for beta S, the true coefficient for the affected state S. By taking an average of beta hat S prime across all the affected states, always treating the state S prime as the comparison, we would arrive at an estimator that's centered around the average value of beta S across all affected states. It's important to note that, however, the presence of a totally unaffected state does not repair the problems we highlighted earlier with the 2-effects estimator beta hat. For the numerical example, we show that even if we add a totally unaffected state to the sample, the 2A fixed effects estimator will still remain centered outside the range of the true coefficients beta s. And this is consistent with what recent papers had proposed, that instead of trying to fix the 2A fixed effects estimator, these papers propose difference in difference style estimators as an alternative estimator that work better under heterogeneous treatment effects. And they include corresponding statistical software that can implement these estimators for different settings. Let me conclude this video series. So linear pattern model featuring a unit and time-fixed FICATs appear in many areas of empirical research, and an active literature studies the interpretation of the 2A fixed effects estimator in the presence of unmodeled coefficient heterogeneity. We illustrate some implications for the case where the research design takes advantage of variation across units in exposure to some treatment. In this case, 2A fixed effects estimator can fail to estimate the average of the unit's coefficients. In particular, when there is no totally unaffected state, the issues identified with 2A fixed effects estimator can actually apply more broadly to any estimator, in the sense that they cannot be guaranteed to estimate a value in the range of the true coefficients. Once we have access to a totally unaffected state or a control state, we can fall back on the difference in difference style estimator to provide a more reasonable estimator than the 2A fixed effects estimator, in the sense that, on average, the difference in differences estimator can be guaranteed to estimate the average treatment effect. Thank you very much for your attention, and hopefully this video series provides concrete examples that can help you think through the identification challenge introduced by treatment effects heterogeneity.